All right, looks like I'm online. I hope not everybody went to lunch already. I'm also ready to go for a pizza, so I will have this presentation for you guys and then jump to have some food for me to enjoy also the rest of the afternoon conference. So this work is called Lost in Translation. So we look at how industrial protocol operate when they translate from one protocol to the other. And so we call it lost in translation because we found like several problems with how this device operates. So they might get lost in translating. So this is a joint work between myself and colleagues at Trend, as well as Luca as independent researcher. So industrial networks are very complex ecosystems. So they are not as simple as they were in the 80s. Nowadays, they run on different layers. So you have like the enterprise layer on the top where you define what your network should do, right? So what your business is about, what you want to produce, for example. This also includes, for example, the cloud and so on. Then you have a control network where you define basically, you have a control server that controls the production, and usually control network run on TCP/IP. And then you have a field bus network, which normally run on serial, and is that part of a network that is directly connected to a PLC and to different sensors as well as motors and so on and so forth. So this is very, very simplified, but can be way more complex than this. This is because each of these network layer may run on different protocols. So if you take, for example, a field network down here on the right, you might have Profibus, EC-Link, CAN-Open, and so on and so forth. So there are many protocols for each of these layers. This is because different vendors have different protocols, as well as because over the years there was been like different protocols being introduced. So this complicates really a lot the problem here in communication. That's why the market has produced over the last, I would say, 5 to 10 years, devices that are called protocol gateways. Like this one you have here with me, right? And you can also see on the screen. So they all come pretty much with few interfaces. For example, here you have like a serial interface. This is a wireless interface. Down here you have an Ethernet interface. So this basically operate as gateways, no? Converting from one protocol to the other. This one you see on screen is exactly the piece of hardware I hold in my hand. As you can see, it's pretty tiny, like 10 centimeters long. And as I said, it has different interfaces, and some of these devices might have debug port, like JTAG, to be able to debug the device. Some other may not have. And yeah, I mean, there are different models on the market. So typical installation is as following. So you have the protocol gateway here in the middle. And what the protocol gateway does is to connect the control network that in this example run on Modbus TCP down to the field network, which runs on Modbus RTU. So as you can see here, there is a PLC, which control a relay, a motor, a thermometer, and other sensor. And since this PLC is running on Modbus RTU on serial, right? It needs to be connected to the control network via gateway that does the translation from Modbus TCP to Modbus RTU. So in this case, you have up here in the right corner a Modbus TCP master node. So the master node is the node that controls a slave node. So in this case, the master node is an HMI, like an interface where the OT engineer can operate and set, for example, the speed of the motor, can read the value of the thermometer, and so on and so forth. So from this HMI interface, you can control the PLC, which acts as a Modbus slave node. What often happens here in an installation, there is an ICS firewall, which monitor the TCP/IP traffic, and in case there are operations that are not allowed, for example, setting, I don't know, like a speed of a motor up to a value which is too high and might damage the motor, the firewall can basically stop such a request. So a common understanding is that protocol gateways are tiny, cheap, embedded piece of hardware. Often they are hidden, somewhere in, server, in a server farm. So they are not visible. Actually, that's not true because this device actually run a fully fledged operating system. Some have a Linux embedded operating system, others have other real-time operating system running. So they really run a fully system, right? And they don't perform secondary tasks as many people think, right? I mean, they're not industrial robots, so they're not like huge robots you can see that are producing something, but they play a very, very important role in the network because if this device crash or have some problems, then all the production gets screwed up because all the traffic go through these devices. So they're basically like a core component to the network. And as a consequence of this wrong common misunderstanding, these devices tend to be overlooked and often not indexed in the list of assets of your company. So in the list of things, like the inventory list, of things, of devices you have in your company. And they might not be correctly, for example, patched, and not be correctly monitored or even misconfigured. So we start our search with the idea to do something new. So in the past, Thomas, you can see here on the left side, gave a presentation at Black Hat US 2018, where he showed that this device might have problems, what we call intrinsic vulnerabilities. For us, not much about finding bugs in these devices, but it's more like studying the technology behind the protocol translation and see what could go wrong when you translate from one protocol to the other, like looking at from the network standpoint, what happened in the translation. And we did it in a vendor neutral way. So we are not finger pointing a specific vendor, but we are studying, as I said, the technology behind these devices. We focus on Modbus because it's probably the most and widely used ICS protocol out there. Has been around for decades, has been, is used everywhere and support both the control network, so the TCP/IP side of the interface, as well as the serial network, what's called Modbus RTU. So we consider 5 gateways from 5 different vendors. As you can see on the screen, we have some from Taiwan, from the East, some from Europe, some from US as well. So we try to be as global as possible, as international as possible. And so the gateways are pretty much all similar to each other, apart that they divide into macro categories. Those of that are real-time gateways, like this one on screen here on my hand, and those of that are data station. So the main difference here is that real-time gateway operate in real time. So as soon as you have a packet hitting the inbound interface, the device translates the packet down to the outbound interface. So there is a one-to-one match, if you want, between inbound and outbound traffic. While data stations are more complex devices, and for optimization and performance reason, they adopt an asynchronous approach. So inbound and outbound are not necessarily in sync. So what happens is that if an inbound interface, for example, receives a read command, for example, to read a value out of a sensor, the device might not query the sensor directly because the device might have already a cached version of the data on the sensor. So the gateway does not wait for an incoming pull request to pull data out of the slave. So the data station regularly pull a slave like a PLC for updated values, keep a local cache, and then update, and then when a request comes from a master, you basically respond to the master. Of course, this more complex configuration requires what is called input-output mapping table, and it's something we will see later in the presentation. So let's see how we approach our research. So suppose we have a researcher like ourselves, right? We want to study how a gateway operates, one out of many, right? So the approach tends to be generic as much as possible in a way that we can reuse the same approach on different gateway products. So what we do, we configure a fuzzer based on what we want to test, like which kind of protocol we want to assess. Do we want to test the gateway from the TCP interface, so in the translation from TCP to serial, or from the translation from serial to TCP? So we configure the fuzzer generates test cases for the gateway, and also monitor the gateway in case there are problems, like the gateway might crash, the gateway might delay the translation, and so on and so forth. So the Fuzzer has already some heuristics for monitoring the device under test. At that point, the gateway, what it does, it receives inbound traffic and it translates the traffic down to a simulator. So a simulator is a piece of code that simulates, for example, an HMI interface as a master node, or can simulate a PLC, a slave node. And it's very important, especially for data station that might not work correctly if there is no simulator attached to the gateway. Then we have a sniffer that collects data, sends such data down to an analyzer that processes the data in real time by comparing inbound and outbound traffic and detecting what potential problems. So let me go a bit in detail on these macro components. So when it comes to the simulator, as I said, is a very important piece of code because it's used as a device. It simulates basically, for example, a PLC, right? So in this example, you have two simulators, one on the left side of the screen, which simulates the master node, and this connected via, as you can see here, via TCP/IP on this address to the gateway. And then we have a slave, which is connected via RTU, so via serial interface, serial port to the gateway. So in this example, the master generate a read coil command. So send the command to the slave by requesting to read the value of 5 coils. So coil is an address of 1 bit only. So that means it's going basically to read the value of the first 5 bits out of the slave, for example, the PLC. So in this case, it sends the request, the gateway translates the request for the slave reply and get to the master. So it's very simple. So this is an example of translation from TCP to serial. Let me use this example to tell you a bit more about how the Modbus protocol look like. So here is the packet that is sent by the master. So it contains a header and information such as the type of protocol, the length of the payload, and so on and so forth. And here you have the payload, which consists of these 5 bytes that are basically, they express the function code 01, which means read data, starting from address 0 for a quantity of 5 register. So what happens when the master node generates this packet get hit the gateway get rid of a Modbus TCP header, which is not present in Modbus RTU, take the payload, compute the checksum, and send such packet down to the serial interface. At that point, the slave reply with 1010, which is actually the data which was on the PLC, and basically the gateway does the opposite. You basically reassemble the header, and you can see here register value 15, which corresponds to what was on the slave. Yeah, so let me tell you a bit about fuzzing. So fuzzing is a very complex argument. We can speak for hours about this. Of course, we don't have time, so I'm trying to just go very high level. So there are 2 macro categories of fuzzers. First one that are mutation based, so they are able to learn the semantic of the protocol, and these are used when you want a fuzz protocol that is, for example, proprietary. For example, Siemens S7 or any other proprietary protocol. In this case, we went for a generation-based fuzzer because Modbus is a free specification. You can download the specification from our website. And at that point, we went for BooFuzz, and in particular, a customized version of the code developed by Youngcraft. I want to credit here. And BooFuzz is super cool because you can basically, if you know, like if you have a specification, then at that point, you can, for example, here on screen, this is an example to fuzz the write single coil request. So a coil used to set a bit on a slave node. So here you can specify here with a block called ADU, the header of the Modbus TCP. You can specify the payload, and you basically define all the different fields, what the different fields are, if they are integer, if they are word, how big, how long, the Indianness of the field. And also you can say if you wanna, what you wanna fuzz. You wanna fuzz all the field, just some of them. Do you wanna fuzz in which, you know, you wanna cover all the address space of the field, or just you wanna fuzz a few random values? You may wanna add like some, down here, for example, some trailing garbage. So like if you wanna make, for example, a very long packet to potentially trigger a denial of service, for example, condition. So it's really cool. I really suggest you to take a look at this Fuzzer. You can also, of course, instrument Fuzzer to monitor for conditions that might be a sign of a crash. For example, you can regularly connect to the device to see the device is still up or not. And in case something is wrong, you can automatically reboot the device if you have a way like to, as we did on our side, to control an intelligent power socket. Okay, Sniffer, we use Wireshark for the internet interface, and IONinja, which is a very cool piece of code to monitor serial interfaces. And then we have basically a code for normalize the output of these tools to be able to compare what comes from the internet interface with the serial interface. In this way, the analyzer can, as I said, automatically detect mismatches and packet drops. I'm not going much into detail on how we did this, otherwise it would take too much time. It's written in the paper. So we have different heuristics for making sure that the inbound packet actually get forwarded, actually get translated to the outbound packet and in a correct way. This is our setup. One of our setups, for example, here we have an intelligent power socket, power strap that it's used to reboot the device in case of crash. We have a serial tap that we use to monitor the serial traffic. We have a sniffer of a TCP interface as well. Then we have an Arduino where we run both our Fuzzer as well as different simulators. That all of this, of course, it's Linux based, so it works pretty well with Arduino. All right, so this is it's first 15 minutes of my talk. It's about what we kind of introduction. Let's now go to the most interesting thing, so what we have found. So let me start with the resource exhaustion. So this is the case in which the device might, for example, reboot, might hang, might have problem on the TCP IP stack. So all the tested device, show such a problem. So it was very easy for an attacker to block these devices, which means like a ransom, for example, a plant, because you can remotely, anywhere from the control network, by just sending few packets, block the device and block basically all the communication down to a field bus network. So here we have a device which operates in 15 minutes. You can see here, 15 minutes, 45 seconds. And so we start fuzzing it. Here on the right, you can see that we generate a test case every second for a total amount of bandwidth, which is only 21 kilobits per second. So it's negligible, it's nothing. But even at this speed rate, we can basically, the device, the Fuzzer here detect, thanks to Procmon, like a crash. In fact, if we connect to the device here, the web interface of the device does not respond. So the device actually just, crash. And so what the system did automatically bootstrap, thanks to this power socket, this intelligent power socket, we made the device reboot. And the device, yes, got up since 5 seconds. And you can see here physical state up again. And you can see that the fuzzing continues. So this is, it's called DG, this device. But all these different of our devices show this problem. But one called Red Lion was actually even cooler, because by sending a single packet, you could basically make the device reboot. So one of these packets is called read coil 0, which means you want to read out of a slave the value of the address number 0. So this device is a data station. So I'm going to describe that later, but just to be briefly mention that this 0 here in data station is used as an index in the memory of the IO mapping table. So it's an index in the IO mapping table. So most likely they made some mistakes with 0. It could be that the index table might start from 1, so the device doesn't know what 0 is. At that point, the device basically reboot. Let me, using here, yeah, VLC, I'm going to show you a demo of this. It's pretty short. So here is basically the device that is beeping correctly. So it's working as fine. So here we send such packet where we say, okay, read basically 0. And you can see the device basically just, you know, crash. You can see down here, there are no more information coming, no more logs coming from the device. There is a beep. The device is actually rebooting down here. It takes about 20 seconds. And now it's up again. You can see down here, when I'm going to send the same packet again, and the device, they see, crash again. So all the LEDs went down and you basically reboot. Yeah. Yeah, pretty scary. All right. So let's now look at the core of our research, that is this protocol translation thing. So how we can abuse a protocol translation to do a large set, to bring a large set of attacks. So first we start testing our device and see how reliable they are when it comes to filtering malformed packets. And it turned out that one of these devices was not able to filter any malformed packet. You can see the 0 here. So we said, okay, you know, probably, you know, this device does not have any, you know, filtering mechanism in place. So some of these packets turn out to have a wrong message lang information. What does it mean? It means that basically in the Modbus TCP packet, there is a field called message lang that is used to indicate how long is the PDU, like the payload. So in this case, the payload consists of 6 bytes. But, you know, the message lang field contains a value of 11. So there is a match between the real lang of the payload and what is expressed in the field of a Modbus TCP header. So this packet was one of the malformed packets that were automatically built by the Fuzzer, okay? So what happened here is that the device did not do any translation. So it did not get read, for example, of header, compute the checksum. So it did not convert from TCP to RTU, but it basically just did the straightforwarding, right? So it basically took the packet as it is and just put it on the outbound interface. And what happened here is that if you have, for example, an attacker that compromises an historian, like a database, for example, where data of the production is stored, you can send such packet down to the protocol gateway. What the protocol gateway does, it forwards the packet as it is to the PLC. So as an example, we have this packet here you can see on screen. This is a packet that has, as you can see here, in function code 4. That means that this packet is a read request. Okay, in Modbus TCP, if this byte is 4, it means that we are going to send basically, by the semantic Modbus TCP is a read request. And we are basically asking to the PLC to give us 70 registers in X starting from this address. What happens is that if this packet gets forwarded as it is on the RTU bus, if we read the same packet by applying the Modbus RTU semantic, basically this packet automatically becomes a write multiple coin request. This is because the function code in Modbus RTU is the second byte, which is 0f. So automatically, basically, we are able to convert a read request into write request. So this is pretty severe, as I'm going to show you in the demo, because if you have a firewall in between that prevent any change to the configuration of your plant, of your network, for example, change the value of a motor or disable a relay or disable a thermometer, if you have a firewall in place that prevent that, then you normally say, okay, you know, I'm relaxed. But you know, here you can basically convert a read into a write. So you can basically follow easily the firewall and you can send a very innocuous packet like a read and turn it into a very offensive packet where you can basically change anything in your network. So let me show you this example here with VLC again. Yeah. So this is our gateway, you know, is this one here. It's operating correctly. This is a web interface. It's configured to convert the Modbus protocol from Ethernet to serial. It's listening on this port for inbound traffic on the Ethernet interface. Now what I'm going to do, I'm going to run the two sniffer, one on the Ethernet interface and one on the serial interface, thanks to this pass monitor application. And then I'm going basically to send the packet I showed you before, exactly the same, like a read request. And you will see basically that on the PLC, which is this one you can see here on screen, something will happen. So the PLC is correctly operating. So it's reading the value out of a thermometer, is reading the value out of a tachometer, is saying that the motor in the production system is operating correctly, and so on and so forth. So I'm going to send such packet down here. You can see the read request, function code 4, such number of address from this address. All right, so as you can see here, as soon as I send the packet, basically the gateway forward the packet as it is on the serial interface. The PLC receives the packet and interprets the packet as a write. So it disables basically the thermometer and the other information and keep the motor running. So that means that the motor is running without a feedback loop. So it doesn't know how much if things are going fine or not. So you have basically a production which is out of control, but it could be very severe. Here I'm showing that from the sniffer, basically it's a push request. That's the packet the attacker sent. And is exactly the same as the packet that is received on the serial side. So there is actually no, as I said, no translation, but a simple forwarding of the packet as it is. All right, so let me jump to data station. So these are more complex devices because they do not work synchronously, but they have two routines. One that basically parse the inbound traffic and set basically values in the mapping table. The second one is basically used, basically monitor the mapping table in case there are changes somewhere in the address of the mapping table, generate the appropriate request for the slave. So take this example here. We have a data station configured as following. So the data station is configured to set a software switch on the slave, like set a bit like 0, 1, whatever on the slave, and set an integer like a critical temperature on the PLC. And these two Modbus commands are mapped to this address you can see here. So address 0, which is 1 byte, is used to control the software, the set software switch, while address 2 and 3, which is 2 bytes, to set the critical temperature. What does it mean? It means that if the device received a request of write to the first address 0, what the device will do is generate a set software switch command. While if you receive the request for address space 2 and 3, it will basically set the critical threshold. Kind of a bit confusing thing. So there are different problems here. The first is that it's a given weird factor things. So basically what happens is that in this device, if the device receives a write coil, I don't know, address 0, it will basically propagate the write coil to the outbound interface as it is. In a data station, it will use 0 as an index in the mapping table I showed you before. So in the mapping table here, down here, basically it's using an index here. So it will not forward the packet as it is, but it will set basically that bit in the address table. That's how these data stations are designed. And the problem is that there is an out-of-bind write condition, and also there is no check on the function code. What does it mean? It means that the attacker can write everywhere in the mapping table and trigger basically any command is configured in the mapping table based on how the mapping table is configured. So let me show you here the input. The input is that an attacker can convert a write coil into write register, as well as a write register into write coil, and can also cause an amplification attack. So it can use a write multiple coil request to generate on the serial side multiple write coil and write register request. Okay, let's go with an example which makes things way more easier to understand because we don't have much time here. I have 10 more minutes. So let's assume there is again, like in a production plant that is configured as following. So there is the admin can set a critical temperature threshold, in this case is 200 Celsius. And then you have basically a plan that is monitoring the temperature, in this case 42 Celsius. No? So what happens is that if these current temperatures go over the critical temperatures, the production, basically the PLC generate, trigger an alarm and block the production. So we assume that this critical threshold is a protected parameter. So there is no way to change such value because because we don't want, someone might tamper with this critical value. So a way in which this implemented is via an ICS firewall. So there is an ICS firewall that block requests to set a critical threshold. You normally do it by blocking a write request, okay, where a write register request, where you want to change basically a value of a register, okay. So we show you how exactly an attacker can actually set such value very high to disable the alarm. So to make sure to make in a way that the temperature may not be able to hit such threshold. And we also show you the opposite, how you can set such threshold very low to trigger false positive. So here it's basically the example. Let me go back. Yeah, here. Moxa camera 1. Yeah. So this is what we built here. It's our testing lab. So that's the gateway. It has the data station we're going to test. It has the two interfaces, Ethernet and serial. The Ethernet is connected either to a Fuzzer or to something basically what simulates the machine controlled by the attacker, where actually the attacking traffic is generated. Then we have, yes, the serial cable, which is connected down here. This is an Arduino that runs OpenPLC that simulates basically the PLC I described you before. And this PLC is connected to a different sensor for the temperature, for example, and it's actually measuring this 42 degrees Celsius, and to the alarm. So this basically simulates, the production. So now here, yeah. So this is what happened on the attack side. So this is how a legitimate engineer would change this critical threshold temperature. It will use this write register command because the threshold temperature is it takes basically a register, right? So value 3000 means 300 because it gets converted in float. It's one byte off. As you can see here, it basically uses this function code 6, which is write register. You can set it back to 200. So now we show how an attacker can change that by means of a write coil. So the write coil is used to flip one bit only, right? So it doesn't make sense because you're basically setting one bit, and thanks to one bit, you're changing an integer. And the problem here is that you're changing basically address 22. So when the attacker generates such request, this 22 is used as an index in the mapping table. So the address 22 in the mapping table of the data station get flipped. And at that point, that value converted in integer is used to set the threshold. So you can see the threshold go up to 1800, which is very high. And this might cause problem because if a production get too high and there is no control, then you're going probably to burn, something, right? But even worse, you can flip, as you can see here, it's bit 23 if I recall correctly, and you can cause an integer overflow, and because you're going basically over the maximum, so it's actually an integer overflow, you set the critical threshold down to negative, and you can see the alarm get triggered. You can see from the PLC interface, the HMI interface connected to the PLC, sorry, and also physically from here. Right? Here you can see on the screen that basically, we are flipping that bit, we do an overflow, and we bring the temperature down to negative. Yeah. Okay, so let's see briefly different techniques we have found to leak the mapping table in order to make such attacks more targeted. Because if you have an understanding of a mapping table, you're not doing a blind attack, but you're doing an attack where you know what you're doing, right? So the first problem we found is that one device encrypts the admin password used to configure the device with a nonce that is guessable. Why? Because the nonce is always the same after reboot, reconfiguration, or update, because it's initialized, if you look at the firmware, is initialized without an initialization vector. You can see here V11 does not have an initialization vector. So it's always the same. So you can use such nonce, reuse it, and authenticate it, basically authenticate yourself to the device and have full access to the device, not only to the mapping table. So the first is the fact that the configuration in our device, the configuration that is dumped is by the device, so that you can dump from the device, is decryptable. Why is decryptable? Because you can basically, here in Python, you can extract the configuration from the traffic. Then you can see that the AES key that is used is embedded as part of the configuration. It's super lame. So we figured out that they don't use a standard AES, but what we managed to do was to basically reuse the library from the firmware, and we basically use such library. We emulate the library with QMO, and we passed basically when we do the decryption, the AES key, which is included in the packet that we dump from the network. So you can basically decrypt all the configuration that come as a SQLite, and then you can dump the mapping table. I want to mention that in the recent version of Moxa, the firmware is encrypted, but the guy did mistakes, because when they introduced the encryption mechanism in the firmware, they basically included the key as well. So if you look at the post here, you can see how you can decrypt basically modern recent firmware of Moxa. And after you decrypt the firmware, you can extract, of course, all the libraries to decrypt the configuration. Then in our case, we found a privilege escalation. So you can log into the web interface where you can, and you go in the debug session where you can ping, devices. And here there is basically a common injection vulnerability, and in which you can run a telnet daemon basically, and this ping thing runs root. So I don't know why, but at that point, telnet runs root, and you can basically connect in to the device, and you're basically root. So you can go from an unprivileged user called read-only to an admin. So at that point, you can do whatever you want. So in another device, we found a memory leakage that allow us to dump part of the mapping table. We are still investigating this problem. So what happened is that you can send basically, you can see here, this is the tag payload. So you can send a request where you're going to ask to read 4 registers starting from address 0. What the device does here, it leak, as you can see, a part of the mapping table called the register 45563, in such a way that basically it dumps the mapping table to the slave, and then you read back such values. At that point, use an attacker, you query again the gateway, and you dump the mapping table. And the address in which of this memory, it's guessable, it's predictable. So you can control which portion of the address space you're going basically to map. At that point, you can basically identify the mapping table and destruct it. Of course, we found a bunch of our problem. I don't have time today, but basically a problem with the cloud. So the lack of encryption, lack of sanitization, broken authentication, and so on and so forth. The fact that you can change the IP address of these devices by a single magic packet, bring the device basically offline, or actually another IP. There are problems with how the device implement different specification in translation. So they don't actually follow necessarily the specification of Modbus. At that point, this might cause problem when you integrate the devices of different vendors, and so on and so forth. So I would say you have to, as a field engineer, you have to consider security as an important aspect in product selection. So recent devices have certain degree of security, while other may not. So try to focus on those devices that have some security capabilities in place. Do not rely on a single point of failure. So don't say, okay, I have an SCS firewall, I'm done, because we have seen how we can basically bypass SCS firewall by converting legitimate packets into malicious. So you might want to include as well other techniques of monitoring your network. And also consider these devices as an important assets. Even if you are small embedded, they might create big problems. So thanks to this resource, we released different vulnerabilities. And now we are at the number of 10 that we disclose via ZDI. Some have been closed. They are actually 0 days. They are not going to be patched. Some other are being patched. Some other are going to be patched. Some are still open. So there is a bit of everything. I want to thank ICS CERT for collaborating with us on this research. And I want to thank you as well for attending my presentation. So I took 40 minutes exactly. And thanks as well. You can follow me on Twitter. If you have questions, I'm open to take questions here or even offline on Twitter. This is a QR code pointing to a link including the paper. So you can also download the paper and give it a read. So thanks a lot. I'm done with my talk. I'm open to questions. Thank you.